Hi everyone, in this Chem Help video we're going to look at how we would demonstrate that a particular species is either a Bronsted-Lowry acid or a Bronsted-Lowry base. To do that we're going to look at some equations that show amphiprotic substances which actually can be both a Bronsted-Lowry acid or Bronsted-Lowry base, and we'll see how they work in solution. We'll also talk about conjugates and how you can label those in a chemical equation. Okay, so how do we show that something is an acid or a base according to Bronsted-Lowry, and how can we also prove that something is amphiprotic? So let's start off with a species such as hydrogen phosphate, HPO4 2-. So can we prove with the use of an equation and a diagram that this substance can act as a Bronsted-Lowry acid? Well, first of all we need to show it reacting with something. Now, of course we could react it with anything that can accept a proton. Remember, a Bronsted-Lowry acid donates a proton and a Bronsted-Lowry base accepts a proton. So any reaction that shows that would be fine. But we can use water as our first starting point. This is the easiest one to demonstrate this particular concept with. Now what we want to show is that the hydrogen phosphate ion is actually an acid. So that means that the proton needs to move from the hydrogen phosphate to the water. And if that happens, then it's an acid, and the water is a proton acceptor, is a base. Now, you can't have any chemical reaction, of course, without something to go to. So we need to show what the products are. Now, the hydrogen phosphate ion, because it donated a proton, will turn into a phosphate ion, and the water accepting its proton will turn into our friend hydronium. Okay, so that's like that. Now, it's an equilibrium, so it's reversible, so it's a weak equilibrium. That means that the hydronium will be able to donate the proton back to the phosphate ion and reform the original substances. That makes the hydronium the conjugate acid. Now, the only difference between the original base and the conjugate acid is going to be one less proton from the base to the acid, so it gains a proton. All right, and the only difference between the conjugate base, which in this case is the phosphate, and the original acid is that it's one proton difference. So the acid loses a proton to turn into the conjugate base, the base gains a proton to turn into the conjugate acid. So if you're ever given a question where they ask you to match up an acid with its conjugate base or a base with its conjugate acid, there's only ever going to be one proton difference. So if you're adding extra atoms like chlorine and phosphate and different things, that's not going to be a pair. The only difference between the original substance and its conjugate, either acid or base, is either one more proton if you're going from base to acid, or one less proton if you're going from acid to base. Okay, so that's the way you've got to remember that. So that equation there and the diagrammatic arrows and the labeling will demonstrate in your question that that hydrogen phosphate ion is actually acting as an acid. Hydrogen phosphate is actually an amphiprotic substance, which means it can act as a base as well. So how do we demonstrate that in the same question? Well, of course, we start off with our hydrogen phosphate, and we might as well react it with water as well, because that gives us a good comparison. Now, this would actually happen in reality. Hydrogen phosphate will donate protons to water and it will accept protons to water. So in this case, in this example, the water is giving the proton to the hydrogen phosphate. The water is now acting as the acid, and the hydrogen phosphate is now acting as the base. So the role has changed. Now this would be happening, as I said, all the time. Different collisions would result in different products. That makes dihydrogen phosphate and hydroxide ions. Now, reversible reaction. That means that the proton moves from the dihydrogen phosphate back to the hydroxide. That's now the conjugate acid. That's now the conjugate base. Again, if you look at the equation, you can see that the base gained a proton to turn to the conjugate acid, and the acid lost a proton to turn to the conjugate base. So that diagrammatic way represents that that particular substance is amphiprotic. It also shows that water is amphiprotic as well, and it's one of the best ones out there for that. Which one happens to a greater degree though? That's where we need to look at our K values. All acid reactions, well, where something is demonstrating an acid, will have a Ka value and a Kb value. So hydrogen phosphate, if you look in certain tables, you never have to remember these. If you look in tables, you can find out the equilibrium constant for when the substance acts as an acid, or the equilibrium constant for when it acts as a base. Now in this case, the acidity constant is 3.6 times 10 to the 13. It's a very, very small number. The Kb is 1.6 times 10 to the minus 7. Still a small number, but not as small. Now that means that whilst these things are always happening in solution, it's much more likely that the hydrogen phosphate will act as a base. Remember, K is equal to the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium. So this second equation with its larger Kb means that the products are more heavily favoured than the reactants. So in solution, hydrogen phosphate ions tend to be more basic than they are acidic, although it can act as both an acid